Okay. So remind me, so have I discussed these with you last time? Because it's been a while since last lecture. Have I discussed about k-fold cross-validation? Yes, okay, good. Okay, so how about handling multiple classes? Have I also discussed these slides already? Yes or no? Have I already gone through these? Yes or no? If no response, I'll assume we have already gone through these because I really don't remember. No? Okay. Okay. So let's start from here. So today, my plan is to, if possible, try to finish all the slides and stop the lecture at around, I think, a quarter to 12, if possible, because I want to leave some more time to discuss assignment 1, assignment 2, and the mini case study. Okay, because it seems like we got quite a number of questions and concerns, okay, regarding the mini case study, etc. So we'll see, okay, how the lecture goes on today. Okay, so this is the last lecture with you, okay, the last few slides. So basically, previously for all the supervised learning model, we are handling only binary classes only. So that is, we have the class label fraud or non-fraud. Okay, those are binary classes. So how about multiple classes? Okay, so that means, what if when we have more than 2 labels? Okay, and of course, you may be asking, why do we have more than 2 labels? Because previously we are handling only the fraudulent case and non-fraudulent case. But sometimes, okay, you might want more than fraud and no fraud. Say, for example, you got something called a suspected fraud. Okay, especially in real world. Okay, so it is not black or white. Okay, so that's why sometimes you might have more than 2 class labels. So that is the reasons that you may also need to handle multiple classes. But I would say, actually, I think in most of the cases, we will stick with 2 labels. Okay, but anyway, so basically, I think all the previous machine learning algorithm that we have discussed already, okay, can be extended to multiple class classifier. So the first one is logistic regression. So if you remember, so for logistic regression, okay, if it is a binary class, the formula is like this, is P over 1 minus P. Okay, these are actually the odds, okay, if you remember. Okay, so if it is extended to more than 2 classes, so the idea is the same. So you can see, okay, but then you need to select what we call the base class. Okay, so say, for example, you just select one of the label, okay, okay, as the base class. Okay, then okay, you can get the formula. So basically, the formula is very similar to the previous logistic regression. Okay, and after reordering, or solving all these formulas, then you will have the probability of each of the class label. Okay, so this is the resultant of the probabilities of all the class label. So basically, the idea is very similar. It's just the formula is a bit different for multiple classes. And the interpretation of all the betas are the same, okay, as the binary class. Okay, so this is logistic regression. And then for decision tree is also very easy to extend to multiple class classification. So if you remember, for decision tree, we need to calculate the impurity, okay, after splitting on a particular node. So for impurity, there are mainly 2 criteria that we have discussed before. One is entropy, the other is Gini. So if we extend the binary class to multiple class, so these 2, So these two are the generalized formula, okay, if we got k number of classes. Okay, so that means if you simply substitute k equals to 2, then it will be the same as the binary class. Okay, so these are simply the generalized formula. Okay, if you got multiple classes. So if you remember, so the calculation of this the splitting node is still the same. So for entropy, we will calculate the information gain. Okay, and for Gini, and then we would prefer a lower impurity for after splitting the node. Okay, so basically the idea is the same. Okay, it's just the formula becomes a generalized formula. So also very easy to extend to multiple class. So for neural network, it is even more easier. Okay, for neural networks, if you got multiple classes, then the output layer, you will have multiple nodes. Okay, so for neural network, these are actually even more easy to extend to cater for the multiple classes. Okay, so I want to give you a case study. Okay, so this is a case study about financial statement fraud. Okay, financial statement fraud. So, but then because I think that this study is a bit, I would not say it is outdated. Okay, but because it is back in 2017. Okay, so maybe the methodology is a bit, I would say more traditional. But anyway, the reason that I want to show you this case study is that, okay, so first of all, in a way, it is very similar when you do your mini case study. Okay, we all start with defining the scope or the objective of your study. Okay, so in this case, in this particular case, so in addition to the financial statement, so that means in addition to simply looking at the financial statement, so this case study, they are trying to check whether there is any other variables or any other attributes that might be useful, okay, for the fraud detection process. So the data source for this data set is coming from some annual reports because they are studying the listed companies. So all the annual reports, the listed companies will be published, okay, and will be publicly available. And then they selected around 300 fraudulent cases. So these fraudulent cases, they selected from the US SEC reports. Okay, so that means these cases are actually confirmed cases. Okay, during 10 years period. Okay, and then they select around 300 non-fraudulent cases. So you can see that they are trying to match, okay, to make a balanced data set. Okay, so if it is a balanced data set already, then you do not need to do, you know, the oversampling, etc. Okay, so this is the data set. Okay, so regarding the attributes, so these are the financial variables. So that means they extract the financial ratios, etc., from the financial statement. And then in addition to the variables, they also extract some linguistic variables. So the linguistic variables are obtained from the annual reports. Okay, so for these linguistic variables include, so in a way, they are just simply doing some frequency counting. Okay, so say, for example, they are counting the number of positive words, okay, in the corporates, in the annual reports, the number of negative words, okay, etc. Okay, but I would say, because again, this is a you know, the research is conducted back in 2017. So by that time, so ChatGPT is not popular, okay, or you know, the handling or the modeling of the language models are not that advanced. Okay, so right now, if you are going to redo it, okay, you can think about it. Okay, so for the linguistic variables, okay, can you extract additional information? Okay, not just counting the positive or negative words, etc. Okay, but anyway, So that means, so going back to the initial objective. So that means when the researchers, when they try to build a model, okay, they want to add some new variables. Okay, so in this case, they have selected some additional linguistic variables. Okay, so in a way, so that means it will align with the initial objective set out in the beginning. Okay, so that means, okay, so they feed the financial variables, linguistic variables, okay, into a list of machine learning algorithm. Okay, so in a way, they are doing quite a lot of trial and error. Okay, I would say they are just trying out on different machine learning model and see which one works best. Okay, so for this case study, I'm not going to go through, okay, the details of the results. What I want to show you is that when you build your machine learning model, so basically you can see that you can try out. So in addition to just trying different types of machine learning model, so you can think about it. So actually they are trying out, say, for example, using all the variables to build the machine learning model, or using only the financial variables, using only the linguistic variables. And then they also use, you know, some ways to select a subset of variables. Okay, so the selection criteria is using correlation. So this is the correlation table. Okay, so this is the correlation table of the variables. So this is also another way, okay, for you to build your machine learning model. Okay, so that means when you build your machine learning models, you can think about whether you should use the whole, use all the attributes in the data sets, or are you going to use only those relevant attributes? Okay, I think that is the point. Okay, so that is the point. Okay, so the other thing that I want to highlight here, so you can see that, so these are the models. So these are the models. So these are different performance matrix. Okay, so you can see that the F-score, okay, the AUC. Okay, so I want to highlight here is that when you present, because, okay, especially for assignment 2 and for your mini case study, so you are required to compare at least two supervised learning model. Okay, so in your report, you should tabulize them. Okay, you should, you know, write your own summary table. Okay, so this is what I want to stress. Okay, so so this is the case study. Okay, and I think that's all for the previous lecture slides. Okay, so let's go to today's lecture. Okay, so basically today, what we are going to talk about will be 3 topics. But as I said, because I would like to reserve some time for the discussion of the mini case study and the assignment 1 and assignment 2. So we'll see whether I could finish all the slides today. So if not, I'll leave some, maybe probably for the support vector machine, maybe I'll leave it next time. Okay, so we'll see. So first of all, is about the insurance fraud scheme. So for the insurance, I think in some of our previous case study, we have also mentioned some of the insurance type. So there are many different types of insurance. Okay, like life insurance, health insurance, automobile insurance, etc. Okay, so for all these insurance fraud, okay, these could be committed by different entities. Okay, so these are actually the entities. Okay, say for example, the insurance agent or the insurance provider, the insurance subscriber, the service provider. Okay, and finally is a conspiracy fraud. So conspiracy fraud simply means it involves more than one parties. So say for example, the insurance subscriber work with, you know, collaborate with the service provider, okay, to make up some claims, okay, to claim the insurance, okay, for example, okay. So these are the examples, okay, for each of the that could be committed by each of the parties or entities. So say, for example, for the insurance agents, so they may be selling policies that is not existed. Okay, so say, for example, because sometimes the customers may be buying an insurance not directly from the insurance company. Okay, they may be buying the insurance through some insurance agents. Okay, so in the past, in a way, you know, usually the customer won't find that there is any issues or problem until, say, for example, I don't know whether you have buy any, say, medical insurance. Okay, it is not until you have to claim the insurance, then you find out that maybe the agent collects your premium monthly, but the agent never, okay, really, you know, pay the premium for you, okay, from for the at the insurance company, say, for example. Okay, so basically, these are some of the examples on that could be committed by the insurance agent or the insurance provider. So the other one is about the insurance subscriber. Okay, so these are actually more easily to understand. So usually it will be some exaggerated claim. So say, for example, maybe, you know, your car got some very slight damages, and then you exaggerated the damage, say, for example. Okay, or you fake your medical history. Okay, in the very extreme case, maybe you fake your death, okay, in order to get the life insurance. Okay, so these are, you know, some of the examples. Okay, so regarding the service providers, so usually I think the very common way is, you know, overbilling. Okay, overbilling. Okay, so or you know, providing some unnecessary services. So say, for example, if you go to see a doctor, okay, the doctor is, you know, maybe prescribing some medication which is not necessary in your case, okay, in order to get a higher pay. So say, for example, okay. So finally, the conspiracy fraud. So as I said, so usually it will be the collaboration between two parties. So say, for example, the patient is working with the doctors to produce some incorrect, okay, or some false medical records, okay, and the car owner work with the repair shops, okay, to make up, okay, some damages, okay, in order to claim the insurance from the company. So I think that this diagram will be going through again and again. So actually for your mini case study, again, it is very similar. Okay, you need to go through all these steps. And very important is you need to define the scope, okay, of the fraud data analytics. Okay, so let's look at the case. So the source paper is here. If you're interested, you can take a look. Okay, so the background is like this. Okay, so in the US, there is a Center for Medicare and Medicare Services. So basically, the Medicare is providing 3 types of insurance, okay, including the hospital insurance, the medical insurance, and the prescription drug coverage. And these 3 types, they are trying to provide, okay, for the low-income individuals. Okay, so this is the background of the data sets. So the objective of the data analysis is they want to try, so in this data set, this is actually an unlabeled data set. So think about it in real life cases. Okay, so so basically this you won't be able to know, okay, which claim is a fraudulent claim or not. Okay, so basically they want to identify, whether there is any suspicious or actual fraudulent insurance in the data sets. Okay, so more specifically, okay, they want to try to find out so whether there is any, if there is any, you know, a health insurance fraud, okay, is it committed by the insurance provider or the insurance subscriber? Okay, so this is the initial objective. Okay, so again, you need to think about, so what are the possible fraud scenarios? So the committing person may be the subscriber and the provider. Okay, so the entities involved is the service provider. So the possible fraudulent actions will be like these, okay, the exaggerated claims, falsified medical history, etc. Okay, so again, so given all these, you will be able to create the permutations, okay, of the fraud scenarios. Okay, so let's go back to the case. So initially, because this is a real case, so the initial data sets actually got quite a lot of attributes, okay? It is nearly 2,000 attributes, okay? Then, so that means if, you know, in real life, you got such a huge data set, so the first thing that you need to check is whether, okay, so whether all these attributes are useful for your data analysis. Okay, but how to decide? So I would always say that go back to your initial objective. What do you want to do? Okay, what is your scope? Okay, otherwise it will be very difficult for you to narrow down. Okay, especially if you are handling a very complicated data set. So anyway, I think that, so first of all, so actually all these are the discovery from the EDA process. Okay, so first of all, they look at the attributes and then they found that basically over half, okay, more than half of the attributes, the entries actually are blank attributes. Okay, that means no entries. Okay, of course, these could be removed. Okay, and then they found that, you know, some of the, even the attributes with values, okay, there are over 100 of them with, you know, more than 50% missing values. Okay, so they decide to remove them. Okay, they decide to remove them. Okay, and finally, okay, they found that there are some attributes with only single values. Okay, I think for the first two, it's easy to understand. Okay, so for the third one, attributes with single values. So can you give me an example? Why do we have attributes that got only single values? So single value simply means that for the attribute, you only got one value. So say, for example, all are ones, all are zeros, all are yes, or all are no. Okay. So can you give me some examples? Why do we have attributes with single values? Any idea? This is a real life database. Okay, so that means it really happens. Okay, because we are not talking about one or two attributes. Okay, so you can see that there is, you know, quite a lot of attributes with single values. So what are the possible reasons behind? Anyone want to try? No idea. Okay, I'll give you one very standard answer. First of all, I'll check whether there is any input human error. Okay, it is possible. Okay, okay, that is one. Because sometimes, and sometimes because you are merging multiple tables and multiple database. Okay, maybe there is, you know, some errors during when you merge different tables or different database. That is one reason. So what are the possible reasons that you will have attributes with single values? Apart from human input error, apart from, you know, while you're joining the tables, then you got some errors after joining. So what are the possible explanations? So think about it. Okay, so what is this data set about? So this data set, okay, is a Medicare data set containing what? Okay, information of individuals and families. Okay, information related to the insurance. Okay, so what are the attributes, what are the possible attributes included in this data set that might have single value? Okay, very good, very good. Okay, but I would say that I don't think the date will be single value. Okay, so if you found the date is single value, then probably it would be an error. Okay, I see. Okay, and your classmates also give a very good example. Is say for example the country code. Okay, because you know this is a data set from United States. So maybe when they input the address, say for example, the address of the individuals, so the country code will be, you know, all be US, then that will be single value. Okay, so these are all the possible reasons why you have attributes with single values. Then, okay, if you are doing the machine learning algorithm, if you are building the machine learning algorithm, so that means actually you need to review. Okay, if you found that there are attributes with single values, what should you do? You need to drop them. Okay, otherwise basically, you know, you cannot gain additional information or insights from these kinds of attributes, right? Okay, so basically, so that's why you need to do EDA, because after exploring the data set, you found that maybe some of the attributes are actually not useful in the next stage. Okay, so the remaining attributes, okay, is still quite a lot, is 200 something. So the next question is, how are you going to select, okay, the useful attributes, or are you going to use all these attributes? So again, because going back to the objective, okay, they have a very specific objective is to look at one particular insurance. Okay, because initially in the Medicare, they got quite a lot of different types of insurance and information. So with this particular scope, so finally, they only select 10 attributes. Okay, they only finally select 10 attributes which is related to the insurance claims that they want to study. Okay, so finally, they only selected the claim number, the beneficiary ID, the claim payment amount, the provider number. Okay, so the claim utilization date count is this is actually the number of days the beneficiary stayed in the hospital. Okay, so it is about the insurance, the hospital insurance. So this is actually the number of days the beneficiary stayed in the hospital, and then there is, you know, there is a distance attribute. So this is actually, if you remember when we talk about feature engineering, okay, so this is actually a new attribute created. Okay, so the distance is calculated by the beneficiary's address and the provider address. So basically, the assumption is, okay, so if, because the US is a very large country, so the assumption is, okay, say for example, if you are staying in New York, you won't go to a hospital in Chicago, say for example, okay? So that's why they also include the distance. And then of course the claim diagnosis, okay, the procedure performed, etc. But you can see for these 10 attributes, only these 3 are numerical variables. Okay, and obviously they are of different scale. Okay, so the number of days, the payment amount, and the distance, they will be of different scale. So that means you need to do, so the first step you need to do is you need to do normalization or scaling, okay, so as to standardize the scale of these three numbers. So in this paper, okay, they have used the this is the Z-score scaling, okay. So basically, they used this formula to scale, okay, all three attributes. So one of the reasons is that we're going to talk about clustering very soon, especially if you want to perform clustering, you want to scale, okay, or standardize, okay, all the variables to the same size, to the same scale, okay. Okay, the next one. Okay, so the data analytics strategy. So basically for the data analytics strategy, it will give you the direction of what you are looking for. Okay, I think, okay, this is some typing mistake. This should be number and normalities, okay? So basically what you are looking for, okay, would be, okay, so say for example, any specific identification. So this usually will be aligned with your initial objective. Okay, so what are the specific information or specific insights that you want to check? Okay, and the other thing, usually you are also checking whether anyone is trying to avoid any internal control. Okay, so the third one, the data interpretation, basically it simply means that you look at the patterns, okay, the patterns and behaviors, okay, the normal patterns and the normal behaviors. So finally, of course, you want to look out for the outliers, okay, for any red flags. Okay, so you will keep all these in mind when you are doing your data analysis. So in this case, so as I mentioned before, the reason that we need to use clustering is that because in real life, you won't know, okay, in the data set, which claim is a fraudulent claim, okay, because you know, there is many incoming transactions, okay, so there is no label, okay, so unlike the previous supervised learning model, you got a fraud label, okay, but now you don't have the fraud label in the data set, okay, so that's why in this case we need to employ some unsupervised learning technique, that is clustering analysis. So clustering analysis is one of the unsupervised learning technique. Okay, so the aim of clustering basically is to group all the observations into different clusters. Okay, so by the clusters, what we want is the homogeneity within the cluster. Okay, so by homogeneity, it means that you want the data points within the clusters to be as similar to each other as possible. Okay, so that is homogeneity. The other thing is because you are dividing your data sets into different clusters. So that means you prefer amount or between the clusters, okay, you prefer the heterogeneity. So that means you want each of the clusters to be as dissimilar as possible from each other. Okay, because if you got clusters that are very similar to each other, then it is not very meaningful. Okay, so these are the characteristics of clustering. So examples of these are actually examples of when and where you can apply clustering. So basically, it simply means you can apply clustering in any of the fraud cases, as long as, say, for example, if you do not have a data set with the fraud label. Okay, so usually it will be a combination of two techniques. Say if you don't have the fraud labels for the data set, so usually what we do, we'll try to do clustering first, okay, to see whether you can form more than two clusters, okay, and to look at the characteristics of each of the clusters. Okay, so clustering. So as I mentioned, so this is an unsupervised classification. Okay, there is no predefined target class. I think that the last two will be, the main issues, okay, or the techniques that you need to learn is because actually you don't know how many clusters there are in the data set. Okay, so for clustering, at the end you need to find out, so what should be the optimal number of clusters. So I give you an example here. So you see the data points, actually they're the same. Okay, so that means you can divide them into 3 clusters like this, or you can divide them into 5 clusters like this. Okay, so whether you should choose 3 clusters or 5 clusters. Okay, so which are the optimal number? Okay, so that is one of the questions that you need to solve. The other question is about the meaning of the clusters. Okay, so even though, say for example, finally you select 3 clusters. Okay, so what are the meaning of these 3 clusters? Okay, so what are the characteristics? So what do these means? Okay, because as I said, it is not unlike those supervised learning model, you already got the labels. Okay, so then you're not very clear whether this is the throttling class, whether this is the throttling class, or whether this is the throttling class. Okay, so the interpretation of the clusters actually is very important. Okay, so first of all, we need to answer the question. Okay, so how are we, so as we mentioned, we want to group the data points with, very high similarity together. Okay, so how are we going to measure the similarity? So for clustering, so usually we will use a distance metric, okay, to quantify the similarity. Okay, so depending on the type of the variables, okay, there are different distance metrics. So say, for example, if this is the continuous variables, so usually we will make use of the Minkowski distance, okay? And then the other thing is if it is a categorical variable, we'll make use of the other 2 index. So for the continuous variable, so this is the formula of the Minkowski distance. So it simply means that this is a distance between 2 data points, xi and xj. Okay, xi and xj. So these are actually the coordinates of xi and xj, okay, over n dimensional space. K equals to 1 to n. It simply means an n dimensional space. Okay, so and there is a p value here. You can see there is a p value here. So depending on the value of the p, okay, the p value, you will get different distance matrix. So the most commonly used p value is p equals to 1. When p equals to 1, we will call this the Manhattan distance. Okay, so what is the Manhattan distance? Manhattan distance is simply, as illustrated in the diagram, is simply like this. So say, for example, if this is a 2-dimensional space, so you are measuring this distance plus this distance. Okay, this is what we call the Manhattan distance. So very easy to understand. So if you substitute p equals to 1, you will get this formula. Okay, you will get this formula. Okay, so it is, so you can get the distance, the Manhattan distance between xi and xj in this case will be 30. Okay, so the distance is simply this one plus this one. Okay, so this is the Manhattan distance. But I think the most commonly used distance is the Euclidean distance. So the Euclidean distance is defined when p equals to 2. Okay, so it simply means that you substitute the p here. Okay, when p equals to 2. So you can see from this graph, so the Euclidean distance is simply the shortest distance between 2 points. Okay, you draw a straight line. Okay, and this is the Euclidean distance. Okay, so the formula is like this. Okay, and then in this case, in this example, the Euclidean distance is 22. Okay, so very easy to understand. Okay, so how about categorical variable? Okay, for categorical variable, we will make use of two measures. One is called the SMC. The SMC is the simple matching coefficient. And the other one is called the Jaccard index. So for the categorical variable, so it is a simple counting in a way. Okay, so you are counting the number of matches, okay, between two observations. Okay, so for the simple matching coefficient, it will count all the yes, yes match and all the no, no match. Okay, and however, for the Jaccard index, okay, so basically the main difference is it will not count the no, no match. Okay, so I'll give you an example in the next slide. Okay, so basically, so in this example, okay, so you can see that, so all these are categorical variables, okay? All these are categorical variables and they have the value yes or no, okay? So you are trying to measure the distance between these two claims. So actually what you're trying to measure is the distance between these two claims, okay? So if we use the SMC, so that means we are counting all the matches between these two observations. So that means all the yes, yes, and all the no, no, okay, will be included in the counting. So in this case, there are two matches here, okay, two matches, and the total number is 5. Okay, so the SMC will be 2/5. Okay, however, if we use the Jaccard index, okay, so the definition is for the Jaccard index, we will not count the no, no matches. We only count the yes, yes matches. Okay, so in this case, there is only one yes, yes matches, okay, and we will not include, okay, the no, no matches. So you can see that now this is 4 only, okay, because for the Jaccard index, actually, we will not include this attribute. Okay, so that is the idea, okay, of the SMC and the Jaccard index for measuring the distance between two observations, okay, when using the categorical variable. So the question is, okay, so what happens if you have actually, so when you look at these, so these are actually the red flags. Okay, so when these attributes, when the value is equal to yes, so that means it will be a red flag. Okay, so it means that, so if you have over 100 red flags, okay, and on average, okay, only a few red flags are being raised, so that means you got many attributes here, okay, over 100, okay, and many of them are no, okay. Actually, most of them are not being raised, okay. So if in this case, okay, if in this case, so which measure would be more appropriate? The SMC or the Jaccard index would be more appropriate. Okay, so remember, we are trying to measure the distance. Okay, we are trying to measure the distance between two observations. Okay, so for those who think that, okay, so we should use the SMC, the simple matching coefficient, to measure the distance. Okay, raise your hands. No? Okay, so for those who think that, you know, using the Jaccard index is more appropriate. Okay, raise your hands. Okay, a few. Yes, good. Okay, so basically we should use the Jaccard index. Why? 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 Why using the Jaccard index is more appropriate in this case, if we got many no-no matches? Why? No idea. Okay, you think about it. Okay, so I'll leave it to think about it at home. Okay, so actually the answer I think in a way is quite obvious. Okay, so anyway, so that is how you are going to use the distance matrix in clustering, okay, to measure the similarity and dissimilarity. Okay, so but in this course, okay, for clustering algorithm, actually there are many different types of clustering algorithm. Okay, but in this course, we are going to cover the k-means clustering only. Okay, so but I just want you to know that actually there are many different clustering algorithm available. Okay, so in future, okay, so maybe you found that there is some limitations for the k-means clustering. You may try to think of maybe using other different algorithms, okay, for clustering. Okay, but I'm not going to go through all the the other types. Okay, so basically we'll focus on the k-means clustering. So for k-means clustering, okay, so k-means clustering, so in a way is what we call a non-hierarchical procedure. Okay, so because as I mentioned before, okay, there is the hierarchical clustering. So but anyway, so it is a what we call a non-hierarchical procedure. So the idea of k-means clustering is you're trying to partition the data points, okay, based on the centroid. Okay, so the centroid is you can think of it. So the centroid is the mean of the cluster, actually. Okay, so basically you are depending on the centroid. Okay, you will assign the data point to the cluster. But I think one of the problem of k-means clustering is that you need to decide on the number of k. Okay, the number of k. So you need to decide whether you are going to have 3 clusters, 5 clusters, 8 clusters, etc. Okay, so you need to specify the number, okay, before you can go on to perform the clustering procedure. Okay, so how to decide the optimal number, the k number. So we are going to discuss it later today, so don't worry. So the algorithm of the k-means clustering is as follows. So first of all, you try to select some of what we call the seed. Okay, so that means, say for example, if we use k equals to 5, so that means you need to select 5 seed to start with. Okay, and then after you select the seed, okay, then you use that seed as the as the centroid of one cluster, and then you calculate the distance, okay, of all the other data points to this mean. Okay, and then for those nearest to the mean, it will be assigned to the cluster. Okay, so this is the idea. Okay, and then after assigning to the cluster, you recalculate the centroid of the new clusters, and then you repeat the steps, okay, until there are no changes to the centroid. Okay, so I'm not going to illustrate in the following slides. So say, for example, we assign k equals to 2. Okay, so that means we try to partition the data into 2 clusters. So because it is randomly chosen, so say, for example, we randomly choose these 2 data points, okay, as the seed. Okay, so these 2 data points are chosen initially as the seed. And then the second step is you calculate the distance between all the data points to the seed and assign all those data points nearest to the seed to the cluster. So then finally you got 2 clusters, okay, because this is the first cluster with this as the seed. This is the second cluster with this as the seed. Okay, so after forming these 2 clusters, now the next step is you recalculate the centroid. Okay, so the centroid now changes for this cluster, now changes. And for this cluster, initial, the seed is here. Now the new centroid is here. Okay, because this is the new cluster. Okay, So after recalculating, now the mean is here. Okay, so that means now you got 2 seed again. Then you repeat the steps again. Okay, so that means now you calculate all the data points nearest to this mean, and you calculate all the data points nearest to this mean. Okay, so after recalculating, now you form 2 new clusters. Okay, so the clusters now changes. Okay, okay, so again, you repeat the steps. Okay, so after forming these 2 new clusters, you again recalculate the centroid. You recalculate the new centroid after forming the new clusters. Okay, so you can see that basically the centroid is now being shifted. Initially, it is at this position. So after recalculating this new centroid, it is now changed to this. Okay, so basically you repeat the steps again. Okay, you calculate the distance of all the data points to these 2 new centroids again. Okay, so the steps will be repeated again and again. And when will this stop? It will stop until, okay, so now you got 2 clusters, okay, and then you recalculate the centroid, and there is no changes to the centroid anymore. Okay, then you stop. Okay, so that is the idea of k-means clustering. Okay, so actually I think the idea is quite simple to understand. Okay, so that's why it is called k-means, because every time it is trying to use the centroid or the mean of the cluster, okay, to try to find all the data points, you know, nearest to the centroid. Okay, so that is the idea. Okay, so the advantages of disadvantages of the k-means cluster is, in a way, I think a k-means cluster is computationally efficient. So you can see that the algorithm is very simple. Okay, it's very simple. And it can be used to, it is very simple to implement. So you can see the algorithm is very simple. And even though you've got a very large data set, it is able to handle. So I think the disadvantages of k-means is, first of all, you need to decide, okay, so what are the number of clusters that you want to partition the data sets, okay? So, and the other thing is, I think for the clustering procedure, so you can see that because every time, so for the clustering procedure, so you can see every time it is trying to calculate the distance between the centroid and all the data points. Okay, so that means even though, say for example, even though you've got some outlier here, it will be included into the cluster, right? So that means for this clustering algorithm, it cannot handle noise or the outliers very well. Okay, so I think that is, also one of the problem with the k-means clustering. Okay, but as I said, because usually this is, you will usually perform this step if you do not have any label. Okay, so I think this is also a very good or useful technique, okay, for you to get the labels first. Okay, so anyway, so going back to this, so how are we going to decide on the value of k? So we are going to talk about the techniques later today. Okay, there are different techniques to get what we call the optimal k value. Okay, so let's take a break and come back in after 10 minutes. So please come back at 10:35. Okay. Okay, let's continue. Okay, so now let's see how we are going to interpret the clustering results. So first of all, okay, so as we mentioned, okay, so after partitioning the data into different clusters, so how are you going to know or interpret the meaning of the cluster? So one of the way, okay, is to do something like this. Okay, you compare the cluster against the whole population. Okay, so for the red bars here, okay, is cluster 1. Okay, so you again, so this is similar to what you do during EDA. So you're looking at individual attributes. So the attributes recency, monetary, and frequency. Okay, so the blue bars here are the population. So obviously, you can see for cluster 1. So for cluster 1, for the recency, okay, so basically, as compared to the population, okay, you got, you know, a higher spike here. Okay, so that means, so say for example, actually I don't remember what this data set is about. Okay, but assuming that, but I think it looks like insurance claim. Okay, so let's assume this is an insurance claim. So recency is how long the insurance is being bought. Okay, so that means the claim is made after the insurance is bought after less than 1 year, 1 to 2 years, 2 to 3 years, etc. Okay, so you can see that for the population, usually, say for example, the first claim is made during 2 to 3 years, okay, or after 2 years. So you can see, okay, but for this cluster, you can see that it is very focused for the during the first year. Okay, so that is the idea. Okay, for this cluster. So this cluster is has a very low recency value. Okay, and then for the monetary value, so say for example, this is an insurance claim. So this is the claim amount. So you can see for the population, so usually the claim amount is between 1,000 and 5,000. But for this cluster, you can see that the claim amount is very focused to over 100,000. Okay, and then for the frequency, okay, so assuming that this is a frequency of making the claims, so actually I would say it is, you know, cluster 1 is quite similar to the population for the frequency. Okay, so this is how you are going to interpret the cluster C1. So that means for the cluster C1, it has a low recency value and a high monetary value. But what does this mean? Actually, okay, so this is the characteristics. So in a way, so this is the characteristics of cluster C1. But you know, but as I said, assuming this is about an insurance claim data set, so how would you finally describe this cluster? Okay, I would say this may be some suspected fraud case that we might need to look into, because as I said, compared to the population, okay, all the claims are being made within a year, and usually the claim amount is quite huge. Okay, so I would say that, okay, there may be, you know, which deviates from the normal pattern of claims. Okay, so for example, this is deviant from the normal patterns of insurance claim. So I may say that there may be, you know, some suspicious activities going on. Okay, so this is how one of the way that you can interpret the cluster. So the other way is using a classification tree. Okay, so that means you build a decision tree. So how to build a decision tree? Because as I said, after performing the cluster, you will have the cluster ID. You will have the cluster ID. So you basically just insert the cluster ID back into your data set. Then that means now you have a labeled data set. Okay, although the only question is you don't know what cluster 1, 2, 3, 4 means. Okay, but then this will be the label. And with the label, you can build something like this. Actually, you can build a classification tree, or you can even build a logistic regression model. Okay, so which is a white box model for you to understand, okay, each of the clusters. Okay, but anyway, so this is also another way for you to understand or to interpret the clusters. So finally, okay, so after you partition the data into different clusters, so similar to when we are doing supervised learning, so how do you know whether the final data model is good or not? Okay, so that means how are you going to evaluate the performance? Okay, so as I said, for supervised learning model, we got a number of performance metrics that you can use. So that is the accuracy, precision recall, F1 score, okay, AUC, etc. Okay, so, but for clustering, I think the problem of measuring the performance of clustering is that there is actually no universal criteria, okay, of, you know, how good is the clustering model. But then we can evaluate the solution from two different perspectives. So this one, the interpretability, we have mentioned it, you know, just now. So that means after partitioning the data set into different clusters, are the final clusters interpretable? Okay, so that is one perspective. So the other perspective is from the statistical perspective. So what does this mean? So that means we are talking about similarity, right? Okay, for a good cluster solution, we would want a high within cluster similarity and then a low between cluster similarity, because it is very obvious. You want the data point within the cluster to be as similar to each other as possible. So that's why you prefer a high within cluster similarity, and you want, you know, different cluster to be as dissimilar as each other as possible. Okay, so that's why you prefer a low between cluster similarity. So basically, these would be the two criteria, okay, for measuring the cluster. Then the next question is, so how are you going to quantify the similarity? Okay, again, of course, we are making use of the distance. Okay, we are making use of the distance. Okay, so statistically, we will use the sum of square error, okay, as the similarity measure. So I think that this formula is very easy to understand. So this is basically, you calculate the distance between X is the data point, M is actually the centroid or the mean of the cluster. So that means you are measuring the distance of, you know, this is actually within the cluster, the distance of all the data points from the mean within the one cluster. Okay, and then this summation sign is simply the sum of all the clusters. Okay, sum of the distance of all the clusters. Okay, so this is the sum of square error. Okay, and with the sum of square error, then you can calculate the within cluster similarity, which is, we call the WSS. Okay, and then you can also use this to measure the between cluster similarity, okay, which is the BSS. Okay, so with these two measures, okay, we can make use of these two measures to determine the optimal number of clusters. Okay, there are two methods to do it. The first one is called the elbow method. So for the elbow method, we are making use of the within cluster similarity. Okay, so the idea is like this. Okay, so the idea is very simple. Okay, so you can see for the x-axis here, okay, so you assign different k values. So that means you start with k equals to 1, k equals to 2, k equals to 3, etc. Actually, you calculate all different partitions, and with different values of k, then you can calculate the total WSS value. Okay, the total WSS value. Okay, so with more and more clusters, okay, so usually the within sum of error will start to drop. Okay, so the idea, it will drop to a point here. Okay, you drop to a point here, although it continues to drop. Okay, but then this is what we call the elbow point. So the elbow point is look like something like this. So you can see the slope here, okay, is much steeper than the slope here. Okay, so this is what they call the band. Okay, for you can find a band here. Okay, so this is the optimal number of clusters. Okay, so that means from this graph, you will choose k equals to 4, okay, as the final cluster solution. Okay, so that is making use of the within cluster similarity. The other method is making use of the between clusters similarity. Okay, so there is, we define a value called the silhouette analysis. So basically it is trying to calculate. So the S value here, it is trying to calculate the distance between the clusters. Okay, so the idea is like this. You got a B and an A. So what is B and A? So basically, so say for example, you've got a cluster here. Okay, and then I is the data point. So you've got a data point I here. Okay, so you calculate, say for example, there is another data point within the same cluster. So the distance between I and any data point within the same cluster is A. Okay, and then you got another cluster here. Okay, and then you got another data point here. Okay, so the distance between I and another data point in another cluster is B. Okay, so what does S mean? So S, the interpretation is very simple. So there is only 3 cases. That is when A is smaller than B, A equals to B, or A larger than B, right? Okay, so when A is smaller than B, looking at the formula, okay, so that means when A is smaller than B, so taking the maximum value, okay, you will have B here. Okay, so you will have B minus A over B. Okay, so this actually becomes this one. Okay, very simple mathematics. So when A equals to B, of course, it will be 0. Okay, because B minus A, if they are equal, then the value will be 0. Okay, so on the other hand, okay, so again, when A is larger than B, then you will have something like this. Okay, okay, and then you will get this value. Okay, very easy to understand. Okay, so in a way, you can calculate the S value for all the data points. Okay, so that is the idea, to get the average distance between the clusters. Okay, so this slide simply, explain the more detailed calculation of A and B. Okay, but I'm not going to go through it because I think in a way it's quite easy to understand. So how to make use of the between cluster distance, okay, to decide on the optimal value. So the idea again is very similar. So that means you assign different k values from k equals to 1. Okay, so in this example, up to k equals to 10. And for each different k values, you will get different silhouette value. Okay, so with this value, so you can see that to get the optimal number of clusters, you will find a peak here. So actually, okay, so you will find a peak here. So, but then you can see that it seems that there are actually many peaks. Okay, if you want to say, okay, so usually, so for me, sometimes I don't think it is very easy to decide. Okay, so sometimes I would say maybe you could, depending how you feel, you may try, say, for example, I may try k equals to 4, okay, to look at the results first. Okay, so sometimes because if I just take k equals to 2, okay, just 2 clusters, okay, it may not be detailed enough, okay, for me to check on the things. Okay, so sometimes I may choose a larger number to see, to look at the results first. Okay, so say, for example, if I choose k equals to 4, and then I found that actually the final cluster results, maybe, actually 2 clusters can be used to represent the final result, then I will go back to use k equals to 2. Okay, so let me illustrate the idea using the case study. So this, okay, so let's go back to our original case, okay, in case you forgot. So remember our original case, we are talking about the Medicare, okay, the Medicare data set. So this is the Medicare data set. Okay, so now we are building a clustering. We are using the cluster analysis to check. Okay, and then we are using these 3 attributes. Okay, to build the cluster. Okay, we are using these 3 attributes to build the cluster. So that means the claim amount, okay, the payment amount, the number of days in the hospital, and the distance between the beneficiary and the hospital. So basically it's the payment, okay, the payment amount, the hospital stay, okay, and then the travel distance. Okay, so this is a very simple statistic summary table, and this is a very simple box plot of these 3 attributes. So again, so sometimes when you are simply looking at the attributes, so say, for example, when we look at the claim payment amount, so you can see that there is an outlier here. Okay, actually, so this is 0. Okay, and then you can see that after 0, there is actually a number of negative values for the payment. Okay, so what does this give you the insights? Okay, so basically, we all know that for payment, it should not be negative amount, right? The value should not be negative. So again, okay, so if you found there is, something suspicious, so first of all, usually what you need to check is whether it is human input error, right? And then, okay, secondly, you need to, if it is a real life case, again, I would say you need to go back to the data owner, okay, to check why there is some negative amount stored in the data set, okay, to check whether these are actually, some fraudulent cases or not, okay? So this is one. The other one, that is, very interesting value is, purely looking at the maximum value of the hospital stay, okay, because this is number of days, okay. But in a year, we only got 365 days. So that means someone is staying in the hospital for over a year, okay. But of course, again, you need to check whether this is, reasonable. Okay, so why someone need to stay in the hospital for over a year? Okay, so of course, finally, when you're checking, those who have spent more than 1 year in the hospital, there is only 28 beneficiaries, then you may look into more details, okay, of these cases. Okay, so for clustering, okay, so as we said, first of all, you need to perform data preprocessing. I think not only for clustering, basically, I think for all the machine learning algorithm, you need to, do some preprocessing about the data, okay, before you put the attributes into the machine learning model. Okay, so that is one. And especially for clustering, you need to standardize the scale, okay, for all the input attributes. And then we make use of the k-means clustering, the k-means clustering method, okay, and they make use of the Silliard score, okay, to determine on the optimal number of clusters. And then finally, you need to interpret the results. So this is actually what we call the scree plot. So as I mentioned before, sometimes you will find more than one peak. Okay, one peak here. Okay, when k equals to 3, there is actually also another peak here when k equals to 7. Okay, so that means you can choose either k equals to 3 or k equals to 7. Okay, but then as I said, sometimes you may want to try, a higher number. Okay, to see what happens first, okay, in case you are missing out any information. So we choose the 7 cluster results. So this is the result of the 7 clusters. Okay, so this is the size of each of the cluster. So you can see that actually cluster 1 make up of most of the data points or most of the observations. So these three, so these three are basically the 3 attributes. So this is the number of days stayed in the hospital. So this is the travel distance. This is the payment amount. So you can see that we are trying to compare the characteristics of each clusters against. So this is the whole population. So this is the whole population. So comparing it with the distribution of the whole population. Okay, so obviously just looking at the results, okay, the graphical results. So I would say these 4 clusters, they look very similar, right? Okay, so the first 4 clusters, they look very similar already. Okay, right? And obviously for the last 2 clusters, they are very different from all the other. Okay, also this cluster also stands out different from the others. But you can see that for this cluster, so these 2, okay, when you are looking at the distance and the payment, so this is also very similar to these clusters. It's just this got some deviation. But for these 2, okay, obviously very different. Obviously, they're very different. Then we look deeper. Okay, so I would say, as I said, so basically for these 4 clusters, they have relatively short travel distance. So this is the distance. So the travel distance is relatively short. Okay, the number of stays in the hospital is relatively short. So the payment amount is also relatively small. So I would say that looks quite normal. Okay, so think about it. Of course, you will try to find a hospital nearest to your home. And because the number of days stayed in the hospital is short, so that's why the claim amount is small. Okay, right? So this looks like very, the average or normal behavior. Okay, and then we look at this one. So for this cluster, you can see that basically the travel distance is short, okay, so which looks very normal. And then you can see that, so this is actually the hospital stay, okay, so that means the hospital stay is longer. Obviously, it's longer than the normal case. And with the longer stay, you can see actually the payment amount is a bit larger, okay, a bit larger than all these. Okay, there is a shift here, so you can see the mean actually is here. So on average, the mean is more on the left. Okay, so that's why you need to check whether this is also some normal cases. For me, it still looks normal. Okay, because given that if you have a long hospital stay, of course the claim amount will be higher. Okay, but of course you need to check, as I said, okay, because previously you found some with extreme, so these are actually extreme cases. Okay, some of them are staying in the hospital for longer than 1 year. Then these extreme cases, then you need to check. Okay, otherwise, I would say this cluster also look like some normal behavior, but just a different normal claim behavior. So finally, the two claims which looks, you know, the behavior is quite different, okay, from the previous two. Okay, so for cluster 3, okay, for cluster 3 here, so you can see that it is very odd because the travel distance is very long. So that means the beneficiary is traveling a long distance to the hospital. Okay, they're selecting the hospital quite far away from home. Okay, and then although the stay in the hospital is short and the claim amount is short, but it doesn't seem, you know, normal. Okay, or I would say that it deviates from the normal behavior. Okay, because as I said here, the normal behavior is short hospital stay, small amount of claim, but also a relatively short travel distance. But for this one, they got a relatively long travel distance. Okay, so it is also noteworthy. Okay, so whether there is something wrong with this group. So finally, for cluster 4, so cluster 4 is a very interesting pattern. Okay, so you can see the claim amount is much larger than all the others. Okay, but the hospital stay is relatively short. Okay, so then, okay, so this is a relatively new pattern. Okay, so as I said before, all the clusters with long stay, and then the claim amount will be huge. With short stay, the claim amount will be small. But this one actually is a small, it is a short hospital stay, but a large claim amount. Okay, so then there may be something wrong also with this group. Okay, so this is how you're going to interpret the cluster. Okay, so that means the final result, now you reduce a huge amount of claim. Okay, so finally to a what we call a more manageable amount, okay, for further investigation. So even for this group, okay, actually cluster 4 only got 40-something cases. Okay, so for 40-something cases, it is a manageable amount, okay, for further investigation. Okay, if you know, someone want to do some further investigation into the cases. Okay, so that is how you do clustering. Okay, so the next step is about how to do clustering using R. I found another data set in Kaggle. Okay, so this is a bank simulation payment data set. Okay, so mind you, so this is not a real life data set. This is a simulated or some synthetic data. But I think this data set in a way is quite interesting. There is a very detailed description about, you know, making use of this data set, okay, and making use of many different machine learning algorithms, and also using clustering. Okay, so for those, because I think most of you comes from the computer science background, if you're interested, you can take a look. Okay, I think that this is a very, in a way, the idea is quite good. Okay, so anyway, we'll focus on the clustering part. Okay, but what I want to show you in this, it is quite similar when you're trying to do your mini case study, or in the future, if you got a data set, what you're going to do. So you can see initially for this data set, this is not a very good data set to start with. You can see for this data set, you only got 10 attributes, although a lot of observations. But looking at this data set, okay, you look at the type, okay, of the attributes. Most of them are of character type, right? So in a way, not very useful for you. Although this is a labeled data set, you can see there is a fraud label here. Okay, the only numerical type is the amount. Okay, because this is a spending, okay, bank transaction data set. Then you can see there is some customer label. Okay, the age of the customer, the gender of the customer. Okay, the zip code. Okay, the merchant ID. So this is actually the merchant ID. Okay, and the zip code of the merchant. and then you got the category of the spending. Okay, so the category of the spending, you got transportation, leisure, sports, hotel, etc. Okay, quite a lot of different category. So I would say this is not ideal for you to start with. Okay, so say for example, if you want to do clustering, you probably need some numerical value. Okay, so how are you going to do? Okay, so anyway, they did some EDA. So after EDA, so first of all, you want to know what are the normal behavior, what are the normal behavior. So after just looking at the EDA, okay, they found that basically for normal behavior, the transactions, the amount usually is very small, okay, which is under $500. Usually the payment for the categories, for the transportation and food transactions, basically no fraud cases, okay? And then for some of the merchants, they also don't have any fraud cases within their transactions. But for the abnormal behavior, so basically the transaction amount is very high, okay? So the transaction category will be related to travel or leisure, okay? And then for some of the merchants, basically all the transactions are fraud transactions. But remember, this is a synthetic data set, okay, not a real life data set. But anyway, just to give you an idea. So now you have an idea what are normal behavior, what are the what we call the abnormal behavior. Then the next question, okay, so after performing EDA, okay, so basically you want to do some feature engineering. Okay, if you remember feature engineering, so that means you need to select, you need to decide on which variables that you need to keep for your next step, okay, or whether you want to, say for example, you want to recode, you do some recoding about the character variables into some numerical variables to make it useful, okay, whether you need to create some new variables, whether you need to remove some of the variables which are not useful. Of course, you need to handle missing value and error value. And for the numerical variables, you need to standardize them, okay, for the next step. So these would be all the steps that you need to do before, okay, you perform your machine learning algorithm. Okay, I think for a lot of the students, I would say usually they skip all these steps. Okay, so they just take it a very straightforward way and, you know, just use all the attributes in the data set and then start building the model. I won't say that you can't do in that way, but usually if you do in that way, usually you won't get a very good performance result for your data model. Okay, so my suggestion is you need to spend more time, okay, before you start building your model. Okay, and okay, let's go back to this case. So actually what they did is that, so this is the original data set, then they do some feature engineering. So after feature engineering, now you can see that actually the variables, they convert all the variables into, you know, numerical variables or integers. Okay, so in a way you can see they are creating, so actually all these variables are newly created, okay, but of course you need to think about how you are going to convert these into some newly created variable. Okay, so I take one of the variable as example. I take the category total transaction here and the category here. Okay, I take these two variables as the example. So you can see in the original data set, you only get the category variable. The category variable originally is of a character type, okay, and the values are ES underscore transaction, okay, or you know, actually the category, the category names, okay. So what we did here is, first of all, we remove the ES underscore, okay, because actually it is not very meaningful. Okay, so this is a very simple step. Okay, so you use the sub function here. Okay, so this is simply substituting the ES underscore with, you know, nothing. Okay, so finally, you will get the category here. So you can see the category values are here after conversion. Okay, so this is the category values. So secondly, we create, okay, actually we create a new category ID. So instead of using the values of the categories, we create a new attribute called the category ID. And then we also calculate the category total transaction. So what is the category total transaction? Again, if you remember when we talked about a feature transformation, okay, so this is actually a binning technique. Okay, this is actually a binning technique. Okay, so we are just doing some counting. So this is actually the frequency counting. So this is actually the frequency count, okay, of how many transactions are being spent on this category. So you can see that most of the transactions belongs to transportation, which I think I would say it is quite reasonable. Okay, so but how to create this table? So in R, so this is the pipeline symbol. Okay, this is the pipeline symbol. Okay, so what does this pipeline symbol means? It simply means so this is the data set. So the data set as the input to the function group by. Okay, so first of all, you group by the category variable. Okay, you do the grouping. Okay, so after grouping, okay, the outputs of the grouping results will be used as the input for the summarize function. So for the summarize function here, I use the N. So the N, as I said, is a frequency count. Okay, so actually you are counting, so you create a new variable, okay, here, okay, and the value of the variable is simply a frequency count. Okay, this is actually a frequency count. So then you get this. And then finally, you also create a new category ID variable, okay, for these categories. So going all the pipeline, the result is stored in category. Okay, so this is simply printing out, okay, the data frame of the category. Then you get the results here. Okay, so after getting these results, okay, so we did one more step. Okay, so basically you want to transform it into, you know, something more meaningful. So in a way, so this is the total frequency. So the total frequency is simply the total number of observations in the data sets. Okay, so you can see that for the category here. So for the category here, so basically you are just dividing each of the category to the, so you're getting the percentage. So in a way, you're getting the percentage of each category. Okay, you're trying to get the percentage of each category. Okay, so that is the idea how you do some feature engineering. Okay, so that is why from the original data set, okay, so initially this one doesn't seem to have any attributes useful, but after feature engineering, now you got a number of useful attributes to input as the inputs to the next step of the machine learning algorithm. Or okay, so in this case, we are going to do the clustering. So for the cluster analysis in R, so these are the libraries that you need. Okay, so to perform clustering analysis in R, so basically you need to handle the missing value first. Okay, and then you need to do some standardization. Okay, or you need to use the scale function to scale all the numerical variable. Okay, and then because for cluster analysis, they need the data sets to be a matrix. Okay, so that's why you need to use the s.matrix function to transform the original data frame into a matrix. Okay, so the codes will be like this. So you can see I scale the data set. But then you can see that while doing the scaling, I remove, at the same time, I remove column 5. So what is column 5 in the original data set? Because column 5 is the fraud label. Because now I am trying to perform a clustering analysis, I don't want the label here. Okay, so that's why I remove the float label. Okay, I don't want to, because if you include the float label, it will affect the result of your clustering results. Okay, because assuming this is an unlabeled data set, so you have to remove, okay, any label in the data set before you perform clustering. Okay, but of course, as I said, this is a synthetic data set, but in real life, you may not have the float label. Okay, but anyway, okay, so after now I got a scaled data set, okay, to continue the next step. So the next step, as I said, you need to convert it into a matrix. Okay, so that's why you use the sdot matrix, okay, function. Then the next step is we do a scree plot. Okay, so this is a scree plot. Okay, so we have talked about using the elbow function. So these four lines actually is equivalent to this single function. Okay, so I think for simplicity, actually you can just use this one function, this single function. Okay, it will be easier. Okay, it will be easier. Okay, but for this function, so you can see you need to specify the method. Okay, so if you're using the elbow method, so that means you use WSS. Okay, and actually you can also use the silhouette method. Okay, if that is the case, you specify another value. Okay, so that is how you're going to plot the scree plot. So say for example, when I look at this scree plot, okay, I take this value as the K because this is the first band. Okay, so this is the first band. Okay, so I take K equals to 3. Okay, so now you decide the K value. Now you can use the K-means because we are making use of the K-means clustering. So for the K-means function, so the first parameter is your data set, and then you specify centers. So centers actually is the K value. Okay, because we selected 3. Okay, so we use K centers equals to 3. So there is also another parameter, n start. Okay, so by default, n start equals to 1. Okay, so what does this means? So the default value n start equals to 1 simply means that, okay, if you remember for the K-means clustering, when we specify K equals to 3, we will randomly find 3 data points as the seed, right? So n start equals to 1 simply means that, okay, I will do it for once. Okay, I will do it for once. I find 3 seeds and then I build the cluster and then it's done. Okay, so for n start equals to 25, it means that I will repeat it for 25 times. Okay, so that means the first time I find 3 random data points at the seed, and then I build the clusters. And then I repeat it again the second time. This time I randomly select another 3 data points. Okay, so I think the reason for this is that, okay, the algorithm is trying to find the best 3 starting points, okay, to build the cluster. Okay, so the algorithm will do it. Okay, so you can just take the default value n equals to 1, or you can I think the usual practice, don't ask me why it is 25, but I think it is the usual practice. Okay, I think anyone tries it before, it seems that this is a very good magic number. Okay, if you use n start equals to 25, then it will find, you know, the best combination, okay, as the starting point. Okay, anyway, so after running K-means, I store the result in this variable. Okay, and then you look at the results. I use the structure to look at the result. So this is the result, okay, of the K-means cluster. So you can see that the first variable, okay, the first variable is actually, okay, the cluster results, okay, of all the records. Okay, so this is actually the cluster results of all the records, okay, with the label 1, 2, 3, actually. And then you can see that, so this is the WSS. So because we got 3 clusters, so this is the WSS of the first cluster, second cluster, and third cluster. And then this is the BSS results. Okay, and then you got the size of the 3 clusters. So the size of cluster 1, cluster 2, and cluster 3, etc. Okay, so this is the result of the cluster. So what is the next step? The next step is the interpretation, right? The interpretation of the cluster. Okay, so the first step to do it is you need to append, okay, or insert the cluster number back into the data set. Okay, so to do it, okay, so basically I make use of the pipeline again. So you can see basically I create a new variable name called cluster, and the value is actually this variable. Okay, the value is this variable. Okay, so these 3 lines simply means that I insert the cluster number back into the original data set. Okay, and then I store the results into this variable. Okay, so the last few steps, so what am I trying to do? So in a way, I'm trying to take a shortcut here. Okay, because if you remember, our original data set actually is a labeled data set with 0 and 1. Okay, so 1 is a fraudulent case, 0 is a non-fraudulent case. Okay, so 1, 2, 3 are the cluster label. Okay, so I just simply want to check, so what is cluster 1, 2, 3? So obviously for cluster 1 will be those transactions with, mostly the normal cases, the normal transactions. Okay, and then for cluster 3, basically it is, mostly contain the fraudulent cases. So cluster 2, a bit of both, I would say. Okay, so but as I said, this is a shortcut, okay, to look at the cluster results. Okay, in the very normal case, actually you should do something like this. Okay, to look at the characteristics of each of the cluster individually. Okay, by looking at the individual attributes. Okay, so that is a better way to do it. Okay, so for me, I think that this is just an illustration, okay, of the final result of the 3 clusters. Okay, so that is the idea. Okay, let me go on. Okay, let me go on to discuss, some of the slides of the SVM, and then let me see when we are going to stop. Okay, and then we'll, have some time to discuss the mini case study, assignment 1 and assignment 2. Okay, so SVM. So now we have discussed supervised learning model. So clustering is for unsupervised learning model, right? Okay, and then so finally, I also want to cover SVM. So support vector machine is also another supervised learning model. Okay, which is again, I think is also quite commonly used. Okay, so for support vector machine, it is a supervised learning model that can be used for both classification and regression. But I think it is mostly used in classification tasks. So the basic idea of support vector machine is to find a hyperplan, or what we call the decision boundary. Okay, so for support vector machine, the idea is to find a decision boundary to separate the data points into different classes. Okay, so that is the idea of the support vector machine. So as I said, so for the basic idea of support vector machine is you want to find a decision boundary. So say, for example, you got 2 classes here, the fraud class here, the non-fraud class here. So the decision boundary in a 2-dimensional space is a straight line. Okay, so if it is a 1-dimensional space, the decision boundary is a dot. Okay, if it is a n-dimensional space, we will call it a hyperplane. Okay, so anyway, so you can see in this case, actually you can have many different decision boundary. Okay, so the question is, so how are you going to decide which is the best fit or which is the best decision boundary? Okay, so the idea is like this. Okay, so say for example, okay, for these two classes, okay, so you want to find the decision boundary that best fits, okay, that best divided the two classes. So the first step is you find something we call the support vectors. Okay, so the support vectors are basically the data points that are nearest to the decision boundary. Okay, so the support vectors basically are the data points that is closest to the decision boundary or the hyperplane. Okay, so these are the support vectors. Okay, and then after you finding the support vector, okay, and then you want to find the margin. So this is the margin of this class. So this is the margin of this class. Okay, and then basically the idea is you want to find the margin here, and the task is you want to maximize the margin. Okay, you want to maximize the margin. So you can see, so given this idea, so what would affect the margin? So basically the support, so any changes to the support vectors will affect the final result of this hyperplane. Okay, the changes of these data points won't affect the classification results. Okay, so basically, but in case there is any changes to the support vectors, it will affect, okay, the classification results. So this is the basic idea. And you can see this is a very perfect and separable classes, right? There is no overlap of these two classes. Okay, but in real life, so usually you will have, you know, these are what we call the misclassification. Okay, so these are the misclassification data points. Okay, so these are the misclassification data points. Okay, so if you have some misclassification, we will say that this is a linearly non-separable. Okay, so these two classes, they are linearly non-separable. Okay, I'm not going to go through the formula here, because I think for support vector machine, the proof is again, you know, quite complicated. Okay, but anyway, for those who are very interested, or for those who are going to take the, I think the data mining, okay, or the machine learning algorithm, I think that you will have more details. But again, so the idea is, so if you have some what we call the non-separable linear linearly non-separable cases, so in this case, there is something called the error term. So this is the error term. So the error term is about the misclassification. And then we also got the C here. So the C here is what we call the hyperparameter. Okay, so by adjusting the hyperparameter C, okay, you can adjust the value here, and then it will actually affect the margin. Okay, you will have a larger margin or smaller margin. Okay, so the hyperparameter C will help you to adjust whether you will have a larger margin, okay, or a smaller margin. So the difference is actually you want to find a balance between having a maximal margin, okay, or you want to minimize the misclassification error. Okay, so this is one of the hyperparameter where we want to do some tuning if you are performing SVM. So the other idea for SVM is that, okay, so previously, so this is what we call linearly non-separable. Okay, so that means the boundary here, is still a linear boundary. So this is still a linear boundary, right? Okay. But then how about this case? So this will be something that we call, this is a non-linear boundary. Okay, so if you got something like this is a non-linear boundary. So in SVM, the idea is like this. Okay, you will make the non-linear classification into something linearly separable. How to do it? Through a mapping function. So the purpose of the mapping function is like this. Okay, so this is a two-dimensional space. You will try to map through the mapping function. You will map it into a higher dimensional space. So say, for example, originally this is a two-dimensional space, and through the mapping function, now this is a three-dimensional space. So this is the z-axis. Okay, you map it. So after mapping into a three-dimensional space, the data points become linearly separable. Okay, using and then you can find the hyperplane, okay, to separate them. So this is the idea. Okay, so this is the idea. Okay, but again, because as I said, because the mathematics behind is quite complicated, so I'm not going to go through into the details, but this is the concept, okay, of SVM. So what is this mapping function? So this mapping function is something we call the kernel. Okay, okay, the mapping function is something we call the kernel. Okay, so the idea is, you can think of it, similar to when we talk about neural network, there is some activation function. Okay, so for the SVM, we got the kernel function. So kernel function basically is simply a mapping function to map, okay, the data point from a lower dimensional space to a higher dimensional space, so that you can make the data points to be linearly separable. Okay, so that is the idea. So what type of mapping function, what type of kernel functions that we can have? So we can have the Gaussian kernel, okay, the Gaussian kernel, okay, the sigmoid function, the sigmoid kernel, or the polynomial kernel. So you can see, if you use different kernel functions, so the result of the boundary, because at the end of the day, the purpose of SVM is to find the decision boundary between different classes. So these are actually three different classes. So if you use a Gaussian kernel, the boundary would look like this. If you use a polynomial kernel, so the boundary is a bit different, will be look like this. Okay, so the results will be a bit different if you use different kernel. And if you use the Gaussian kernel, you can see there is a hyperparameter gamma here. So there is a value gamma. Okay, there is also a parameter gamma here, which you need to do some tuning, okay, before you can build your SVM model. Okay, so about the gamma value, okay, so you can see you can have a very large gamma value or very small gamma value. So the effect is like this. If you have a very small gamma value, you will have a loose boundary. Okay, so this is what we call a loose boundary of dividing three classes. If you have a very large value of the gamma, then you have what we call a very tight boundary. Okay, so the final result will be a very tight boundary. Okay, so you can see the boundary will be, it will be trying to stick to each of the classes, the boundary. Okay, so this is the difference. Okay, if you use different gamma value. The other hyperparameter that we mentioned before is the C. C actually is the cost. Okay, so as we said, C basically is the trade-off between misclassification and the margin. So again, if you have a very small value, okay, then you have a very large margin. Okay, if you have a very large C value, then you have a very small margin. So the difference is, okay, with a very large C value, with a larger margin here, So that means you allowed more misclassification. So that means you allow more errors. Okay. So with the a larger C value here, so you have a very small margin. Okay. So that means you don't allow, okay, many misclassification. Okay. So that is the difference. Okay. Using different values. So the next question is, so how are you going to decide on the optimal value for C and gamma? Okay, so again, so that means for SVM, you need to perform hyperparameter tuning first, okay, before you actually build your SVM model. Okay, and the idea is I think if you remember, we talked about, I forgot, neural network and decision tree. Okay, the idea is the same. Okay, so that means you now, instead of just purely using training data set and testing data set, you need a validation data set, because the idea is you need to build. Okay, so that means first of all you define a set of values for the gamma, a set of values for the C. Okay, so usually these will be the combination. Again, don't ask me why you choose these two sets. So in a way, it is common practice. Okay. So you begin with these two sets of value. Okay, and then okay, you use the combination. Okay, and then you build many different SVM models. And every time you use the validation data set to evaluate the performance. Okay. And then finally, you find the optimal pair. Okay. So the optimal pair will be based on the performance results. Okay. Using the validation data sets. Okay. So after you get the optimal results, then you use the optimal pair to build your SVM model. Okay, so that is the idea. So finally, how are you going to interpret the SVM model? So basically, SVM is also a black box model. Okay, so similar to neural network. So that means you can use all the previous methods of interpreting neural network to interpret SVM. Okay, so that is the idea. So for SVM, I think as I said, basically, it is also a very commonly used machine learning method. I think one of the reasons is that it works very well. Okay, if you got a very clear decision margin, okay, decision boundary for the classes. Okay, and in a way, it is very effective. Okay, if you got a very if the dimensionality of the data set is huge, okay, in a way. Okay, so but I think the problem, you know, not problem. So some of the disadvantages of the SVM is that basically it cannot handle noise very well. Okay, because you can see, okay, so back here, so basically it will include everything. Okay, because it is just simply trying to find the decision margin. Okay, so the decision boundary. So in a way, it will try to include all the data points in each of the class. Okay, so that means even though you got some noise, it will be included in one of the classes. Okay, so in a way, it cannot handle noise very well. And also because actually it is computationally very intensive if you are using some very complicated kernel functions. Okay, so these are some of the disadvantages of SVM. Okay, I think I could finish all the slides here. Okay, so just a few slides left. Okay, so first of all, okay, so how are you going to use SVM in R? So mind you, so for SVM, the library is this one. Okay, so you need to load the library first. Then you need to tune, as I said, you need to do some tuning of the hyperparameter. Okay, so this is the function for tuning the hyperparameter. So I am using the same data set, okay, in the previous lecture, the credit card fraud, if you remember. So this is a undersampled training data set. And then I assign the value for gamma and cost. Okay, so these two combinations of values are actually these two. Okay, actually these two. Okay. So this is the gamma value, this is the cost. And then after running the hyperparameter tuning, I store the result in this variable. Okay, so and then for this variable, I just look at the best combination. Okay, so the best dot parameters, okay, is the attribute storing the results of the gamma and cost. Then you can see the gamma is 0.5 and then the cost is 5. Okay, so this is a combination for you to build the SVM. So this is not the SVM model yet. Okay, so this is just the hyperparameter. Okay, so the next step is to build the SVM model. So you use the SVM function. You use the SVM function. Then you can see I specify the kernel. So I specify the kernel equals to radial. So radial is the Gaussian kernel function. And then the gamma, I use 0.5, which is found here, 0.5. And then cost equals to 5. Again, so I found the value here. Okay. So after building a model, I store the model in this variable. And then again, I use the predict function. Okay, I use the testing data set. Okay, and then I use the model, and then I store the result in this variable. And I can use the function confusion matrix. Okay, I can use the function confusion matrix to look at the performance results. Okay, so you can see basically using the confusion matrix function, it will print out, okay, the confusion matrix table and the performance matrix here. Okay, so this is the results. So again, as I said, okay, when you're doing your assignment and mini case study, don't just screen cap this. Okay. Okay, so I think I put it nicely in the report, especially when say for example, if you are comparing two machine learning model, okay, don't just screen cap the results and then it's done. Okay, you should tabulize the results. Okay, you should tabulize the result. If you don't remember, okay, let me try to find. Okay, okay, so actually you should do something like this. Okay, you tabulize the result. Okay, don't just screen cap the results. Okay, you need to tabulize the results. Okay. Okay, so let's take a brief break. I want to leave around 30 minutes for the mini case study and assignment. So please come back at 11:50. Okay, at 11:50, and then we'll start the discussion. Of course, if you think you don't have any questions about the assignments and mini case study, actually you can leave. Okay, but if you want to ask some questions, and then you can stay. Okay. Okay. So first of all, any questions after assignment 1? Okay, you should have submitted your assignment 1 already, right? Okay, so any questions about assignment 1? No? Good. Okay. So anyway, I think assignment 1 is not that difficult. Okay. So although I just want to share a bit of the commonly asked questions by the other classes. So basically, the students are very concerned about, the number of pages. Okay, we do set a page limit. Okay, and there are penalties if you exceed the page limit. Okay, so, but okay, I think our TA already mentioned that for any graphs, especially for EDA, you can put all the graphs and figures into the appendix. Okay, so those won't count. So similarly, so for the mini case study, okay, there is also a page limit for the mini case study. Okay, so if you got a lot to write, okay, just put those graphs and figures into the appendix. Okay, that is one. So the other one is about feedback or the grading of assignment 1. Because this year we got an extremely large class. Basically, we got a total of 3 subclasses for this course. So that means we have a total of, I don't know, nearly 400 or over 400 students. So you can imagine the workload, okay, for grading the assignments. So having said that, so that means our TA will take quite a lot of time. Will need, okay, quite a long time to grade all the assignments. So don't chase for the grades of your assignment. Okay, when it's done, okay, she'll publish the grades. Okay, but in the meantime, just be patient. Okay. So secondly, is about assignment 2. Okay, so basically assignment 2, you can see for the mini case study and for the 2 assignments, we are using the same data sets, which is the Enron case, right? So that means in a way, I intentionally designed the assignment to be like this, so that, okay, if you complete assignment 1, assignment 2, so basically it will be very easy for you to complete the whole mini case study. Okay, so my suggestion is, so assignment 1 is passed. For assignment 2, okay, before you work on assignment 2, my suggestion is you really, really need to think about what is the objective of your mini case study before you jump into building your machine learning model. Okay, I think that is in a way quite important. Okay, of course, if at this stage you are still very confused, you have no idea how to set the objective, simply to meet the deadline for assignment 2, okay, you can just, build any 2 supervised learning model and submit your results. Okay, that is also okay. Okay, but my suggestion, because some of the students are very concerned about getting good grades, okay, of course I will ask also, what is your definition of good grades? For me, pass is a good grade. Okay, but anyway, so if you really want to get very, very good grade, okay, for your assignment, okay, whatever, you really need to think about, so what is the objective, okay, for building the 2 machine learning model? Okay, you can have many different objectives. If you got no idea, go back to the lecture notes. I think in the previous lectures, every time I gave you a case study, and in each of the case, there is some kind of objective. If you got no idea, so see if you could get some idea from those case studies. So that is my suggestion. That is one. So the other one is, when you are planning for the objective, don't make it very, very general objective. Okay, try to be more specific. The very general objective is, okay, you are building a fraud detection model. Okay, for me, that is not a good objective. Okay, it is not specific enough. Okay, so in a way, if you want, okay, you know, your work to be good, okay, you need to be more clear about what you're going to do. So the other thing is also about building the machine learning model, because I think for the 2 other classes, some of the students, they are already working on the machine learning algorithm, and they come to me and they ask me, why is the performance not good? Okay, or why is there, you know, some overfitting problem? Okay, so my answer is, so first of all, I don't really need you to build a perfect machine learning model. Okay, so for all the assignments, there is no standard or model answer. Okay, I think more important is you know what you're doing. Okay, the other thing is, if you found that there is some overfitting, what should you do? Okay, so say for example, you build, you use random forest to build, okay, your machine learning model. Then at the end, okay, you found, it seems to you that there is some overfitting problem. So what should you do? Build another model. Okay, no, no. Okay, so my suggestion is, okay, if you got overfitting, so why do you have overfitting? Okay, so what is the definition of overfitting? Overfitting is that your machine learning model overlearns the data set, the training data set, right? So usually I would say you go back to the data set. Okay, so by going back to the data set, what I mean is, okay, so what are the attributes and what are the data that you put into the model? Are you just blindly putting in all the attributes into the model and do the training? Okay, or, okay, as we said today, if you still remember about the case study, okay, you need to do some feature engineering, or sometimes you call the data preprocessing, okay, before you jump into building the machine learning model. Okay, you need to rethink. Okay, so take, okay, let me go back. Actually, we mentioned about the case study today. I think that is a very good example, because of course, when you look at the Enron data set, okay, so say for example, when you look at the Enron data set, are you using all the variables? Okay, or are you selecting some useful variable? Okay, because you need to think about it. Okay, don't just blindly put everything into the machine learning model. Okay, because if that is the case, I guarantee you won't get a good result. Okay, and of course, you also need to, so one of the way you select a subset of those useful attributes. Okay, so the other thing is, you also need to think about whether you can divide or categorize your attributes into different, you know, categories or types, and you have a try. Okay, so, and for assignment 2, what I allow you to do is like this. Okay, so I already said you need 2 supervised learning model, right? By 2 supervised learning model, it could be, say for example, you're running random forest or neural network, or say for example, you're using the same machine learning model, but you are trying different techniques or different, you know, attributes. Okay, I also count these as more than 1. Okay, machine learning model. Okay, just to make it in a way easier for you. Okay, so having said that, so that means when you plan for your mini case study, so again, say for example, you select a subset of variables, or after doing EDA, you found some of the variables actually, you know, for you doesn't make sense or not useful for the next step. You can drop them. Okay, but you need to give the rationale behind. Okay, what I need you to do is not to do things randomly. Okay, every step should be planned, should be well thought. Okay, I think that is the idea behind. Okay, of course you can do some trial and error. Okay, for the case. Okay, but then, okay, so for me, there is no absolute answer. Again, because some students ask me, okay, whether I should drop, okay, some of the attributes. So usually my question is why you want to drop the attributes. Give the reasons behind. Okay, so I think that is the only requirement for the mini case study. So as I said, we do not need you to tune the performance to be very good. Okay, but of course you need some reasonable performance. Okay, so even though if finally maybe you come up with a machine learning model with not so good performance, you try to find the reason behind, any explanation why you cannot get a good performance. Okay, so I think that is enough. Okay, I don't think you need to spend a lot of time to do tuning, okay, of the performance model. But of course, if you got time, you could do that. Okay, but if you don't have time, okay, if you got the results, just try to explain, okay, based on the results, what is happening, why you got such a result. Okay, so I think that is the purpose of the mini case study. Okay, so any questions regarding the mini case study or the assignment 2? Because you are the computer science, most of you are the computer science students, so in a way I think it is not so difficult for you, okay, for this mini case study. Okay, but remember for the mini case study, so apart from those data analytics, you also need to answer some of the non-data analytics questions. Okay, so in the mini case study. Okay, so read through the mini case study carefully. Don't miss anything. Okay. Okay, good. So I think for the remaining 2 lectures with me, okay, I think you still got two more lectures with me and 1 more lecture with Annie. Okay, so for the remaining 2 lectures with me, basically for all the machine learning algorithm is done. Okay, so what is remaining is the next lecture we are going to talk about some statistical technique, okay, including Benford's law. Okay, and then the last lecture with me, it will be about social network analysis. Okay, okay, so if you still got any questions about the mini case study or the assignment, okay, you can still ask me, okay, in the next lecture. Okay, okay, good. Okay, I think that's all for today. So I'll see you next week. Okay.